Today we'll take a look at Taylor and Maclaurin series. These are sort of special types of power series. We'll discuss what they are, how to write them for a function. We'll discuss the radius of convergence again, and we'll look at applying properties of power series to those sorts of Taylor series too. So a definition here, don't panic, right? We can take a function and write a power series that represents that function using this definition, and we call it a Taylor series. We'll set this center at a, just like we saw previously. Right? If we create a center at a, that means we're going to have a factor of x minus a to the nth power in our power series. And the coefficients of those polynomials will look like this. We'll have the sum from n equals 0, have to start at 0, to infinity, of f, and this is n in parentheses, this means the nth derivative of f, evaluated at the center a, divided by n factorial. That's going to be the coefficient for each term. So I like to list out the first few so you can kind of see what it looks like. For n equals 0, that's this first term. For n equals 0, the 0th derivative of f is just f, evaluated at a, divided by 0 factorial, which is equal to 1, times x minus a to the 0, that just becomes this constant f of a. Then for the second term, when n equals 1, we get the first derivative at a, divided by 1 factorial, which is still 1, times x minus a to the power of 1. Those two terms by themselves should look like a linear approximation if you've done that before. Essentially what we're doing is just an infinitely big polynomial approximation for this function. So the pattern continues. We look at the second derivative at a divided by 2 factorial times x minus a squared. You could keep going, 3, 4, 5, so on. And that's going to be what we call the Taylor series. We'll build some. One other special case, if we know the center is at 0, so when a equals 0, we have another name for it. We call it a Maclaurin series. You can still call it a Taylor series, but it is a special case. This is also considered a Maclaurin series. I'll kind of use the two interchangeably, but you can always call them Taylor series if you like. So for this Maclaurin, center of 0, I put the formula up here. We have f of x equals e to the x. Try to determine that series, write it out, and then look for the radius of convergence. So let's try it. To do this, I went ahead and I find a lot of derivatives first because we know we're going to need them, right? We need the function itself, the first derivative, second derivative, third derivative, so on and so forth. So find some derivatives. The good news is they're all e to the x. This is an easy one to start with. And so no matter which derivative we take, if we evaluate that derivative at 0, we're going to get e to the 0, which is simply 1. This is an easy one, right? That's making it so that all of these terms, all of these coefficients in the numerator are all going to just be 1s. So all we need to do is worry about the factorial and the x to the n parts. Right? We said that these numerators are all going to be 1 in this case. So we have f of 0, that's 1, right? Plus, that's divided by 0 factorial times x to the 0, which is all just 0, or 1 divided by 1 times 1. The second term, we've got the derivative at 0 divided by 1 factorial times x, second derivative at 0 divided by 2 factorial times x squared, so on. So we know we're going to end up with f of 0, which is 1. The first derivative is 1, 1 over 1 times x is x, and so on. We're going to end up with this series, which we're coming full circle now. Try to write that in summation notation, right? That's x to the n divided by n factorial. And we know that that's just going to be equal to, right? That should theoretically be equal to this e to the x function that we were starting with. As far as the radius of convergence, right? Remember, this is our infinite series that we wrote. If you do the ratio test, it works out just like we've done previously. Right? We take the n plus 1 term divided by the nth term, flip and multiply, simplify, we get absolute value of x over n plus 1. I didn't write the limit here, but we're setting that limit. That approaches 0, which is less than 1, so it converges for every x value. The radius is infinitely large. Another piece of terminology, a Taylor polynomial, as opposed to a Taylor series, is just a part of a Taylor series. Right? It's the Taylor series of degree n. Right? So we write t sub n of x. That means the Taylor series of degree n. So t2 would be a quadratic. t3 would be a cubic. In other words, that's including terms using the first n derivatives. So t0, that would just be the linear, or excuse me, the constant f of a, right? T1, that would be the first two terms of the Taylor series. That would be the linear approximation. T2 would be the quadratic approximation, and so on. As we mentioned earlier, if we were to do an infinitely large Taylor polynomial, that is essentially the Taylor series. So let's try a Taylor polynomial. It works the same way mechanically as what we just did, right? Let's look at T3 of x for this function, natural log x. We're going to center it at 1 instead of 0 because the log of 0 doesn't exist. So we have our formula. We can follow that. So based on definition, let's write that T3, that third degree, that cubic polynomial. So we'll start with the first term. You can use this basic summation notation, or you can start by these, right? F of a is the first one. F of 1 is just log 1, which is 0. So actually that first term is 0. For the second term, that's when n equals 1. We find the derivative. The derivative is 1 over x. And evaluate that derivative at 1, we get a value of 1. So our coefficient for the second term would just be 1. We need a few more derivatives here. In fact, we need 2 more derivatives, so we'll find the second one. The second derivative is just using the power rule now, going to be negative 1 over x squared. And so when we plug in 1, we get negative 1. Our third derivative would be positive again, but 2 over x cubed. And so when the third derivative evaluated at 1 is just going to be 2. So we don't need to go any further since we only want that finite Taylor polynomial of order 3. And so to list it out, we can do it, right? We've got, following the formula, f of 1 plus f prime of 1 times x minus 1, so on and so forth. So we'll plug in those coefficients that we just calculated. The first term goes to 0. The second term, there's that coefficient of 1. The negative 1 here. This 2 comes from the 2 factorial in our formula, times x minus 1 squared. And then we've got plus 1 third, right? That actually was simplified from 2/6, right? We do 2 divided by 3 factorial, which is 6, which simplifies to positive 1/3 times x minus 1 cubed. You could keep going if you wanted to list more terms of the Taylor series, but this is your third degree, since it's cubic, the third degree Taylor polynomial. This sounds worse, but it's not. Let's look at the fifth degree Taylor polynomial for f of x equals sine x, and we'll center it at 0. First, we can list out some derivatives. That's what I like to do, right? F of 0 is just sine of 0, which is 0. The first derivative of that function is cosine x, and evaluated at 0, that's a coefficient of 1. The second derivative is negative sine x, which becomes 0 at x equals 0. The third derivative becomes negative cosine, so we get negative 1 as our coefficient. And then the fourth derivative is sine, back, and we've kind of looped around now, and so that's going to become 0 again, and you can see how that pattern continues. And that's pretty cool, I think, right? The coefficients of this Taylor series are going to follow that pattern that you see of derivatives for sine and cosine. So the fifth degree polynomial is what we want. That could have up to 6 terms, including a constant, but it's not, right? We know that 3 of those are going to just be zeros. So we're only going to have 3 terms in this fifth degree polynomial. And so plugging them in, right, f of 0 is 0, f prime of 0 is 1 times x, and so on and so forth. That second one is going to be 0. The third one, the third degree term, we're going to end up with a negative 1 there, so we have minus x cubed over 3 factorial. The next one's 0, and then x to the 5th over 5 factorial. We can actually get rid of the ellipsis here. This would be your fifth degree Taylor polynomial. If you kept going further, that's going to, eliminating the 0 terms, it looks kind of neater like this, right? That would be your fifth degree polynomial, but you could continue that on if you wanted to write out the Taylor series. Let's try one more. So here we've got the Taylor polynomial T2 for a more complicated function, e to the 2x times sine pi x, and it has a center of x equals 1. So let's try it. If we want to know the second degree polynomial, we're going to need the first derivative and also the second derivative. So our function, if you plug in 1, we get negative e squared. If we find the derivative, this is getting pretty messy already, right? The derivative is going to require a product rule, and it looks like this: e to the 2x times the derivative of sine pi x, which is pi cosine pi x, plus the other part of the product rule. We have the derivative of e to the 2x, which is 2e to the 2x times sine pi x. And then we need a second derivative too. But first we'll evaluate this at 1, right? So for the first derivative, plug in 1, we get negative pi times e squared. So we've got 2 of those 3 coefficients that we need. We also need the second derivative evaluated at 1 though, so we need to calculate that. It looks like this. It's a little messy, but you can kind of verify with some product rules how that works out. When we evaluate it at 1, we get simply negative 4 pi times e squared. And so that Taylor polynomial of order 2, again, we don't necessarily need that ellipsis here, but we can say that this is approximately, if we get rid of the ellipsis, this is approximately the constant term, that was this one, f of a, that's negative e squared, plus the linear term, f prime of a, is negative pi e squared times x minus a, which is x minus 1, plus the quadratic term, which was this one, right? We do negative 4 pi e squared for our derivative value, divided by 2 factorial, times x minus 1 squared. You could do this for a lot of common functions, and we'll investigate more of these later too, but don't memorize all of these, but you can access this table when you need it. Take a look. These are just some common ones that you'll see, and there are others, but these are the most common ones, right? You can actually use the definition we talked about to verify any of these. It's kind of fun to do, actually, if you want to try that. But these are some common Taylor series or Maclaurin series that you can use for pretty frequent functions. Next time we'll start with this 1 over 1 minus x and modify that a little bit, and then also look at some others.